Hi, and a very warm welcome. Uh, my thesis is in the field of automotive manufacturing and studies closely a process called sheet metal forming. Now, I've tried to keep the presentation at a higher level so all of you guys can follow through, and also included some more detailed discussion slides for later. Automobiles are quite complex structures. Here's an exploded view of a commercial car today with the different components it has. If you compare a car from over 100 years ago versus today, there has been not much of a change in the basic structure. It has four wheels, a body to join it, an engine, steering, etc. Although there has been an increase in the complexity of these cars, they have, in terms of electronics, material, design, and of course, offering better performance and safety. Over the years, manufacturers have been driven by certain manufacturing goals, such as to reduce production waste, reduce lead time, increase profits, increase market shares. And on the other hand, customers have been demanding higher quality, better features, and at lower costs. Not just the number of cars produced worldwide have increased, as shown in this graph, but also the desires of customers has increased. Take a look at this picture. Every Mini coming out of the factory is unique as customers are seeking tailor-made products. Thus, industries have been forced to rethink their strategies of finding new ways to improve the processes. Now, concepts like zero-defect manufacturing, first-time right production have gained popularity. And over the last decade or so, industries have been collecting more and more data to improve their processes, to be able to derive hidden insights. And this trend has only augmented further with the dawn of the fourth industrial revolution, as is commonly known as Industry 4.0. To summarize, there's pressure to do more in less time and at lower cost. Now, sheet metal forming is one such challenging manufacturing process used to produce the body components of an automobile. When I say body components, it is the door, hood, roof, etc., as you see in this picture. The production of these components starts with a sheet metal coil, which is fed into a blanking line to produce a blank. Then these blanks are then fed into a press line, and in several steps, you have the final part. In essence, sheet metal forming transforms a blank into the desired shape. So the basic underlying principle is this. The tools, that is the blank folder and the die, hold a blank with desired amount of pressure, and then a punch plastically deforms it to a certain shape. Now here is a video showing one of the steps in the manufacturing. So you have a blank that's fed in from here, and then the forming happens, and then it is fed to the next step where other trimming, restriking operations happen. So here is the sheet input, and the tools basically form it. Now the tools used are quite huge in size, cost millions of SEK, and involve large forces. Just to give you a perspective, that's a human standing in the press plant. Now, if you were living in Olofström, where these plants are situated, you definitely know when one of these machines are operating. So in order for manufacturers to justify the high investments for these tools, it is crucial to have efficient and large volume production. Although this is challenging, and two crucial aspects while manufacturing is the product quality and process performance. Product quality refers to the geometrical precision of the output part, and process performance is the ability of the process to consistently produce products with desired part quality, and without any process interruptions. This is easier said than done, and a lot of challenges are involved. For example, there are varying production conditions due to variations in input material properties, the thickness, variation in the tool temperatures, and friction conditions. Also, this process is very complex in nature. So it involves complex phenomena such as material non-linearity and tool deformations and tribology conditions. And there are also several variables involved in shaping the output product quality. Hence, it is common to have some issues such as spring back, fractures, or wrinkles in the final part. So the aim of this research is to attain a deeper understanding of the challenges and the opportunities in ensuring desired product quality and process performance within sheet metal forming, and also to see how inline measured data, that is data measured in the process, together with simulations, can be used to improve this understanding and predictability and the performance of these processes. So the research question is framed such: how can inline measured data combined with process simulations aid in the understanding of sheet metal forming process? Design research methodology has been used to structure and guide the research, since it allows both understanding and improvement of a situation. In other words, DRM allows to look at a particular situation and find a solution for it. In contrast to traditional sciences, where, for example, in medical science, where you conduct experiments on a specimen and then generate knowledge. It has different stages aimed at defining the overall goals, understanding the problem, developing the intended solution, and also evaluating that solution. So then I looked into this research case of this press line producing the front door inner of Volvo XC90, and this is produced in 5 manufacturing steps, starting from a coil to the final part. And the most critical or the error-prone step is the major forming step, which is then studied. So I started off with these with preliminary inspection by visiting the shop floor and having discussions with technicians in there. And it was found out that issues such as wrinkles, fractures, and springbacks occurs during this production. And it was suspected that this is caused due to varying tribology conditions during production, variations in the input material because the input is supplied from different suppliers, and also variations of the tool temperature and deformations. And today these are dealt by experts on site who have been working with these machines for long and through trial and error gained a lot of expertise. And the usual way to solve it is, for example, tweaking the tool forces, or reducing or letting the temperature of the tools drop, or altering the surfaces of these tools, or even replacing it. And these measures or procedures are costly, halt the production process, and might also generate additional problems, which is not so good to have. Now, there's also this inline measuring equipment in the press line which measure the oil amounts, the type and the distribution on these sheet metal coils, which was fed into the production. So here is an interface of how the reading is shown. The red regions show higher distribution of oil, while the others have low distribution of oil. And it was not sure as to if these affect the output quality. One major challenge for the experts now solving problem is the ability to assign or to determine the right production conditions, right product process settings to deliver correct output. And this can be linked to the lack of knowledge of the interdependencies between parameters and their influences on the output product quality. Hence, we decided to conduct a simulation-based investigation to explore this further. The first step is to have a simulation model. To be useful for this, simulation model needs to accurately represent the studied reality. Hence, complex phenomena occurring in reality needs to be catered for, such as elastic press and die deformations, dynamic friction conditions prevalent in reality. Today, simulations use a constant friction model, whereas in reality, it is otherwise. Also, we decided to include inline measure data, that is lubricant amount in this case, and also model the material model for this. The simulation is run with nominal production conditions and essential to validate it before being used for investigation. And this is usually done by comparing results predicted from simulation with that in reality. Here is an animation of the tools forming. This is played in real time versus the actual blank then forming in incremental steps. Yeah. So once a simulation model was derived, the next step is to build a simulation investigation. That is, we selected a few design parameters: duplication amount, material properties, and Blankholder force, and assigned or generated values for these using a design or experiment strategy. And then the investigation runs several simulations assigning different values to these parameters and predicting results. So the results showed that the lubricant profile affected the predicted part quality, and it also showed that including data from the production into simulations increased the model accuracy. It allowed such investigation also allowed to see for different values of the input how the output is affected. To summarize, it showed the potential to improve the understanding of the parameter correlations and the effect on the output part. Although it was found that while incorporating this data from production into simulations is quite challenging and tedious. For example, a lot of points for the lubricant amount. And it also requires further data processing and configuration tasks before being incorporated. And the simulation softwares today provide limited or no features to facilitate this. Hence, a further study investigated this further and proposed an automated strategy, which was inspired from a server-client model. Server, the controller, controls clients to execute various tasks. In this case, the server launches a numerical computing platform to process data. Then the output from that is fed into the server, after which this output launches client 2, which is a CAD software for a data configuration before being used into the simulation model. I'll not get into the details of this, but to summarize, the results showed that such a procedure reduces the overall modeling effort in building or in incorporating data within these simulations. And it is quite necessary when you have a large set of data, such as in this case. So the results thus far showed the potential of simulations and inline measure data to improve the understanding and predictability of these processes. Although using this understanding in the production process faces additional challenges. Now, if you look at the current procedure in most manufacturing process, is that you have an input, then some sort of sensor to measure this input, and these measurements are more for monitoring purposes to see if the parameter value has crossed the threshold, etc. And if it does, they stop the process. Then you have the manufacturing process and the output. And the output is usually inspected visually, and not every output part is measured, but instead, for example, 5 and 2000 are taken to a separate measuring station where coordinate measuring machines measure these. And if there are some errors found, it is experts who manually adjust the process. Based on the literature reviewed and the previous research conducted, we propose a framework which implements a hybrid data and model-based approach, where you have an input to the process and you have a measuring station. And based on these measurements, a process control system adjusts the process or the manufacturing process, and then the manufacturing conducts its operation. There's an output measuring station which measures the output, and then you have the final output. Throughout the process, sensors collect data and send it to this monitoring platform, which is responsible for parameter supervision, fault detection, diagnosis, and process health monitoring. And then this is used in the process control system to enhance the next steps or to improve the next steps of the manufacturing. In conclusion, the research draws attention towards the need to move from phenomenological-based insights to more structured, investigation-oriented approaches. It shows that inline measured data combined with process simulations hold the potential to improve the understanding and predictability of sheet metal forming process. And to facilitate this, accurate simulation models, systematic investigation procedures, and automated strategies are useful. To be able to use this understanding in real time, a framework is proposed which implements a hybrid approach, catering both for disturbances in reality, but also using the knowledge derived from these simulation models. For future, it's interesting to validate this approach further, implement it and test it in a lab-scale environment, and then also see how the results obtained from the part considered in this research are applicable to other parts production, and also how these results are applicable to other domains outside automotive. For example, kitchen sink manufacturing, you have sheet metal forming employed there as well. And then highly interesting is also, now since we have knowledge about these manufacturing facilities, how can we use this improved understanding to design better products in first place? That's quite interesting also for the future. I would like to thank my supervisors, Mats from Volvo Cars, and the funding support for this research. Thank you.